So this week, I think you have watched the lectures. So the week's content was mainly based on equilibrium equations and think related to stress vector and and also related to mode circle. So we will look at a few problems. So that like very simple problems, which will be which will give you an idea how to do the assignment problems which are prescribed in the assignment 2, I guess. So first we will start with this problem. So given following, find the following quantities for the given state of stress at a point. So first we have to find the stress vector, and then we have to find the stress vector on a plane whose normal is inclined at 60 degrees from the x-axis, and then we have to find out the magnitude of normal stress acting on the surface, and then magnitude of shear stress is given. So first we will see how uh, we get a stress tensor. So if we have any body, and if we take a small infinitesimal point from this, and if I zoom out this point, this will be like a small cube. I'm just assuming like because I am taking I will assume rectangular coordinate system here, which is x, y, and z. So I am taking a cube here, a small cube. So for this small cube, there will be stresses acting like this: sigma xx, this is sigma xy, which is the shear stress, and sigma xz. And if we go here, it is sigma yy, and it is sigma y, sigma yx, and it is sigma yz. And on this face, there will be normal to this, there will be sigma zz, and there will be sigma zy, and we have sigma zx. So this is called the state of stress at a point, and I can write this state of stress like this as a tensor. So stress is a tensor quantity, and that you might have gone through in the course. So here we have sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, and we have sigma zx, sigma zy, and sigma z. So this tensor gives us the state of stress at a point. So using this, we can calculate the stress at any plane which is which is at a certain angle. Like if I give any plane at some angle, let's say theta with respect to this axis. So there can be many planes, infinite number of planes. Based on the angle, I can get the stress, what is the normal stress and what is the shear stress acting on that plane. Uh, so this gives the whole information about stress acting at that point. So, and using this, I can get whatever the stress is acting at different uh, planes which are at different inclinations, which is theta here, that can be found out. So in this problem, so here there is we have a 2D case here. So only we have this is x and y, and we have 10 megapascal, and we have 5 megapascal, and we have 10 megapascal here, and here again we have 5 megapascal. So in this problem, this this row and this column will not be there, because this is a 2D case, and simply there is no z direction here. So all the components which have z will be can be simply eliminated. So one more important thing we have to note is whenever we write uh, whenever we write stress component, like stress component of a stress tensor, so we write like sigma xx or sigma xy like this. So in this, the first the first index denotes the plane. It denotes the plane on which the stress is acting. This component of stress is acting, and the second index denotes the direction in which the stress is acting. Here also same. This is plane and this is direction. So always remember, first is plane and the second thing is direction. So let's say I have shown this, right. So in this in this element like this, if I write, so this is origin and this is, let's say, x, y and z. So this plane this plane is x plane, because it is, if I show it like this is this plane and it is on the x axis, and this plane is perpendicular to the x axis. That's why this plane will be called as x plane, or you can say the normal of this plane is parallel, or like, or it is lying on the x axis. That's why this plane is x plane, and that's why normal to this, whatever the stress acts, that is sigma xx. This is acting on the x plane and this is acting in x direction. And if I this stress, this is sigma x and sigma y, sigma xy. So this is acting on the x plane again, and it is acting in y direction. And this is, if I take this in this direction, this is sigma xz. So again acting on the x plane in z direction. So this is the orientation which we use. So if so, this is the q, small q, and this is the x. So that's how we write. We take the notation. So whenever you guys do this, you should be careful. You should carefully observe like how these notations are being written. So first index always denotes the plane, and the second index always uh, denotes the direction in which the stress component is acting. So here this is a 2D element, and they have given that this is x and this is x direction, this is y direction. So if I want to write the stress vector here, the stress tensor, sorry. So stress tensor is the 10 megapixel which is acting away from the element. So always we take whenever the stress is acting away from the element as tensile. So tensile is taken as positive. So I'll write sigma xx. This is 10 megapixel. So then after that sigma xy. So there is no shear stress acting on this element anywhere. So I'll simply take it as 0, and all the z components will be 0. So no need to take them. I'll simply put that as 0. And sigma yx is also 0. And I have sigma yy, which is again tensile stress, and it is 5 megapixel. So this is how we write a stress tensor for the given problem. So the next question is stress vector on a plane whose normally is inclined at 60 degrees from the x-axis. So I'll just take the diagram again. This is the x-axis, let's say, and if I take a plane like this, and this is a plane which is, let's say, at 60 degrees inclination, which has been given from the x-axis. So I know what is acting on the x plane, y plane, and z plane. Now I have to find out what are the stresses acting normal to this plane, and also shear stress, whatever is acting on this plane. So to do that, first I have to uh, find out what is the normal is. So we have the concept of direction cosines for getting the normals. So direction cosines are whenever we have orientation xy, let's say xy system, and there is, let's say, some vector n, and it is making an angle of 60 degrees. Let's say this is alpha, and it is making an angle of 30 degrees with the y-axis, and let's say this is theta. So the direction cosines of this normal can be given as cos alpha and cos beta. These are the direction cosines, and I can write the normal, unit normal, as cos alpha I cap cos beta plus cos beta theta. So here the direction cosines can be written cos 60 I cap, because it is given 60 degrees. And just so the thing is, this is the normal to the plane, and this is the normal which is at 60 degrees, and this is the plane on which we have to find the inverse stress. So this is the plane slight correction. So plane, and this is the normal to the plane, and normal is always at an angle of 90 degrees with respect to the plane. So no, plane and normal are perpendicular, so we know that. From this I have to find out what are the stresses on this plane. Okay, This is this is the problem. So what is the normal stress and what is the shear stress on this one? That we have to get. So now I know the direction cosines. From that I'm getting the uh, normal. So cos alpha is cos 60 and cos beta is cos 30 and cos beta jk. So what is cos 60? Cos 60 is root 3 by 2 and cos 30 is, sorry, cos 60 is 1 by 2 and cos 30 is root 3 by 2. This is taken. So this is the normal, uh, unit normal written in vector form. So he has given that normal of the plane is at a angle of 60 degrees from the uh, x-axis. So from this angle, I can get the unit normal by using the direction cosines. So direction cosines are written like this. So direction cosines are simply whatever there are axes in your coordinate system. Here we have only two axes, that is x and y. That's why I'll take this is the normal or any vector is at a angle of alpha from the x-axis and beta from the y-axis. And if you have z-axis, let's say, then you can take alpha, beta, and gamma. Then these three, the direction cosines. If this is into three-dimensional thing, then the direction cosines are cos alpha, cos beta, and cos gamma. So always remember that sum of squares of this direction cosines, cos square alpha plus cos square beta. If you have also z-axis, then the summation of these three is equal to 1. So cos square alpha plus cos square beta plus cos square gamma. So here only we only have cos square alpha plus cos square beta plus cos square gamma. So I think someone has joined now. So we are solving this problem. So you just take note of this first question. Find out the quantities for a given state of stress at a point, and this is the state of stress given. For that, we have to find out the stress vector and stress tensor, and then we have to find out the stress vector on a plane whose normal is inclined at a angle of 60 degrees from the x-axis. So just giving an overview for you. So now we know the normal. We have calculated the values. Normal we know. From this, we have to find out the stress vector on acting on that plane. So in order to find out the stress vector acting on that plane, we know Cauchy's formula. If you have seen the lectures, there is Cauchy's formula. Stress vector can be given as stress tensor, which we have got. This is the stress tensor into n. So this you can say dot product also, dot product of stress tensor and the normal. And here, because I have only a 2D system, I'll just write like this. Okay, stress vector can be denoted like this with an arrow. So you can write it like that too. So I have 10, 0, 0, and 5. This is the stress tensor. Because it is in 2D, I have removed these two parts. So, and I have this normal, and the components of normals can be written like this. 1 by 2, this is 1 by 2 in vector form. This is the thing. And if I write it like a matrix, so a matrix with one row or one column can be called as a vector. So that also you can. So I can write it like this: 1 by 2 and root 3 by 2. This is the normal and this is the stress function. So if I multiply this, I'll get again this is a 2 by 2 matrix. Stress tensor is a 2 by 2 matrix, and this is a 2 by 1 matrix. I'll get a 2 by 1 vector. So, and this is the, if I multiply both these things, whatever we get 5 and 5 root 3 by 2. So this is the stress vector acting on that. Okay. Remember that this is not normal and shear. This is stress acting on that plane. This is the plane, right? So this is the plane, and this is the normal, and this this is this 5 megapascal, and this is this 5 root 3 by 2 megapascal. So these are stress acting in x direction, and this is the stress acting in y direction. So this is the stress vector which we have got for this plane, which is having a normal which is 60 degrees inclined with respect to the x-axis. So if you take the components with respect to this normal, again you can get the stress vector normal to the plane and stress vector which is tangential to the plane, which is the shear stress. So the next part of the problem is the same thing: magnitude of the normal stress acting on the system. So in order to get the magnitude of the normal stress, again the C part. So magnitude of normal stress is simply, if I write this is magnitude normal stress can just be taken by using the dot product of this. So we have the stress vector and we have the normal vector. If I make the dot product of these two, I can get the normal stress. So so this stress vector can be written as phi I cap plus phi root 3 by 2 j cap, and I know this normal again we have calculated 1 by 2 I cap plus root 3 by 2 j cap. So if I do this dot product, so I can simply get dot product is I think I don't know, I don't have to explain this dot product thing. So you can simply, or again, or you can say we can just write it like this: pi root 3 by 2, okay, 1 by 2 root 3 by 2. So if you multiply this two matrices, so this the same thing, this is the dot product can be written as transpose T transpose into N. So in matrix form, it can be written like this. So whenever you have a single column, it can be called as a vector. So remember this. So this is a vector. This is the traction vector or stress vector transpose. So transpose column vector becomes a row vector. And if you, this is the dot product. Dot product can be written like this also. So finally, you will get, if you multiply, the normal stress can be written as 6.25 megapascal. So I think you guys have the calculators. You can simply calculate multiply these both matrices and you'll get the answer. So again, I'll just summarize. This is the problem which we are solving. Finding out uh, different first we have to find out the stress tensor for this uh, diagram which is given. State of stress is given and you have to find out the stress tensor, and then we calculate the stress vector on a plane whose normal is inclined at 60 degrees, and then we calculate the magnitude of normal stress acting on the surface. So we have calculated the magnitude of normal stress acting on its surface. Now we have to calculate the shear stress acting on the surface. So okay, so this is the plane and this is the normal. So earlier we have calculated this dx we have calculated the stress vector. From this we again have calculated the stress which is acting normal to the, so sigma n we have calculated using both these components, and doing the dot product. Now we have to calculate what is the shear stress acting. So in order to calculate the shear stress, we again have a simple formula which is, so the magnitude of stress vector square can be given as shear stress, magnitude of shear stress plus magnitude of normal stress square. So I think you all know this. I okay, so I'll just give this same diagram. So the resultant of Tx and Ty, let's say this is the normal vector. The resultant of Tx and Ty is, let's say this is acting like this, and which is our stress vector, Tn stress vector. And from this, we have to break down this into normal stress and shear stress. So you can simply look like this. This is a triangle. So vectors, I think you all know. This is sigma n and this is tau, and resultant is on the hypotenuse. So I think basic vectors everyone knows. So sigma n square plus sigma tau, magnitude of sigma n square plus magnitude of square, and is equals to hypotenuse square, which is the resultant. So vectors, basic vector calculations, you should all I think are comfortable. So now I can say shear stress. I don't think we need this. Shear stress can be calculated like this: magnitude of normal stress minus magnitude of resultant stress, and taking the root of that we will get the shear stress. So think the magnitude of we'll first calculate what is the magnitude of normal stress, because we haven't calculated it. sorry, magnitude of the resultant stress, and this can be written as, we have this vector, so pi square plus pi root 3 by 2 whole square. This will give you 6.61 megapascal. Okay. So this is the magnitude of this, or you can say this is the magnitude of this vector, the stress vector, resultant stress vector on the plane. And we have the magnitude of normal stress, which is simply 6.25 megapascal. So we have to substitute in this to get shear stress 6.61 square minus 6.52 square, and I ultimately I'll get the shear stress is equals to 2.16. So this is how we get the shear stress. Shear stress acting on the plane. So again I'll draw the diagram. This is the plane and this is the normal. So here we got the normal, the shear stress as 2.165 megapascal and the normal stress as 6.25 megapascal. So if you take the resultant of these two and get the magnitude, and if you take the resultant of this txn and tyn, both should be same, because we are taking the components and different in different directions. Here we have taken the component of stress vector in normal direction to the plane and tangential direction, which is also called the shear direction or shear stress. So I think the problem is fully solved now. So if you have any doubts, please let me know. You can turn on your voice, turn on your mic, and please let me know if you have any question.
Hello, sir. This is
Yeah, yeah,
Akshay.
yeah.
Sir, might be there is some mistake on a shear stress equation. Uh, can you please scroll down?
Okay. This equation,
Yeah,
yeah,
yeah, this one.
yeah, yeah.
shear stress is equal to under root of uh, ये मैं ख्याल से माइनस ऑफ नॉर्मल स्ट्रेस आएगा.
Oh, yeah, 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 yeah. So this is I've written the reverse of it.
Yeah, yeah.
So this is total stress vector, the resultant stress vector minus. Okay, so it's fine.
Yes, sir.
Here I have written correctly. Yeah. So this is the problem which we
Sir,
have solved.
actually, I'm getting a problem in calculation. If you check the final answer, then can you please scroll down, sir?
In the shear stress,
Yes, sir. See, last में
yeah, yeah,
in the calculation of shear stress,
yeah.
if you putting a under root of अभी normal stress मेरे को आया 6.61.
Hmm.
So okay, okay. Normal stress, shear stress. Ha, now it's correct, sir. Sorry,
Yeah,
I
yeah.
got a
So,
mistake. Thank you, sir.
Okay, okay. Yeah,
Now
yeah,
it's
fine.
correct. I thought कि नीचे भी equation में wrong लिखा है, but
No,
you
no.
write the correct. I got confused, sir. Thank you, sir.
Ah, only the formula I have written wrong.
Yes, sir.
Okay. Does any others have any problem? Or like if you have not understood some part, or if you want any clarification in this, you can ask, because this is a problem solving session and it is intended to help you. So don't hesitate. Like we are just here for learning. And if you have any kind of doubt, don't feel ashamed of anything, and can just ask. Okay, fine. So yeah, is anybody asking any question? So, yeah. Okay. Okay. Next, I think the problem has been solved. Problem has been solved. We'll go to the next question. Just making it larger much. So in the next problem, I think you guys have uh, studied about equilibrium, I think, in the second lecture of the week. So equilibrium. So we have these two stress tensors, and here we have to find out whether these stress tensors follow the equilibrium equations when they are subjected to some elastic deformation. So whenever there is deformation, there is stress. So due to that stress taken at any point on the body, you if you put the x and y coordinate, you will get the state of stress at that point. So we have to find out whether these stress tensors are satisfying the equilibrium equations. So if they satisfy, these stress tensors are possible. If they don't satisfy, we can say that these are not possible. So these are some uh, things. So first we have this. We'll take the A part. So we have sigma equals to C1x plus C2y, C1y minus C4x 0, C5x minus C1y, C3x plus C4y 0, 0. So this is also a 2D problem, but whatever it is written, we'll take it. And if I take the individual components of this, I have sigma xx equals to C1x plus C2y, and I have sigma xy equals to C5x minus C1y, and I have sigma yx, this part, sigma yx equals to C1y minus C4x, and sigma yy equals to C3y plus C4y. I have written it correctly. Yeah. So all the other things here are 0, which is sigma zx, sigma zy, sigma xz, sigma yz, and sigma zz. All the components of z, whichever are there, those are 0. And now whatever uh, what we have to do, we have to check if this system, if this stress tensor, whatever is given here, is satisfying the equilibrium conditions, which are, I think, which you have, sir has explained in the second lecture, as I've said. So, if this stress tensor satisfies those equilibrium conditions, then, as I've said, it will satisfy, and it is possible. It is a possible stress tensor. So we basically we have two equilibrium equations, the two equilibrium conditions. First, we have the force equilibrium conditions. Force equilibrium conditions. So in force equilibrium, we have three equations because again, like uh, compare, we'll generally take a 3D case. So in 3D case, we have three force equilibrium conditions. So we have dou sigma xx by dou sigma dou x plus, you can write like I can simply write like sigma xy, but we know that sigma xy is a shear stress which is acting on the plane. I'll write it as sigma tau xy. So dou tau xy by dou y plus dou tau xz by dou z plus any body force. Let's say I'm writing it as capital X, body force, or I can simply write it as, okay, just not to mess up with I'll write it as body force as bx, body force per unit volume. This is, and similarly, the next force equilibrium equation can be written like this: sigma dou sigma yx by dou x plus dou sigma again I can write like tau, just shear stress. So tau yx sigma yy divided by tau y plus dou tau yz divided by tau dou z. And the last force equilibrium equation would be sigma zx divided by sigma x, dou tau zx divided by dou x plus dou tau zy divided by dou y plus dou sigma zz dou sigma zz divided by sigma z. Again, here also we have body force in y direction and body force in z direction. So here there is no mention of body force. So that's why I'll assume all these body forces are also negative. Body forces are 0. So body forces are something you can say like if there is magnetic force acting on the body, and also there is gravity acting on the body, or any other thing like uh, electrical potential or something like this. All these forces are body forces, uh, and generally we write body forces as force per unit volume. That's why I have taken Vx, Vy, and Vz. I think these are, I think, uh, not necessary here. Just if you don't understand, just take like there are no body forces. And you know body force, body forces are, as I've said, units are force per unit volume. And you have surface forces. Surface means surface traction. Then we say like that can be taken as Newton per meter square or force per unit area. Traction forces will maybe x. Okay, okay. So this one, right? So this one I'll explain how it will come. So this is tau xy. Okay, I have drawn the state of stress here. Okay, I'll draw it again. Draw it again. So this is some small infinitesimal cube. Okay. Okay. This is the x plane. This is the x plane. The blue one. This is the y plane. And this is the z plane. Why I'm saying these are x, y, and z planes is because this is the orientation which I'm taking. This is x, this is y, and, this is y, and this is z. So this plane is perpendicular to the x-axis. That's why it is a x plane. And this plane is perpendicular to the y-axis. That's why this is the y plane. And this plane is perpendicular to the z-axis. That's why it is a z plane. So this is sigma xs, sigma yy, and sigma z. Okay. Now I have told you how we write the notations. First, we take the stress, the plane on which it is acting, which is sigma tau x. The plane is x plane, and the direction of the stress is in y direction. That's why I'll write it as tau x. The similar thing when I take this stress on the y plane, shear stress on the y plane. This is tau, and this is in the y plane. That's why this is tau y, and it is acting in x direction. That's why this is tau xy. Okay, I think you got how we write, right? Yeah. Okay. This thing becomes equal, which we will see, like sigma xy, tau xy will be equal to tau yx. That's why we sometimes people just interchange like tau xy and tau yx. It doesn't matter because both are equal. That's why we'll write. But here we have to be specific while writing the equations because this is important for this problem. Okay. In other thing, uh, in other problems where it is not required, you can simply write like x, y, or y, z interchangeably. So we got the three equations. Now we have to submit this whatever the components are we have given. We have to submit sigma xx. So do sigma xx by do x. So if you get it, we'll get C1. C1 and just C1 plus do tau xy divided by tau y. So tau xy or sigma xy. So if I differentiate with this with respect to y, I will get again simply C1. And The third part, we don't have any z components, it is 0, and we don't have any body force, so it is 0. And if I x, oh sorry, this is as I've said, do this is the thing. So this we have to okay again. Just I'll just try it like this. So x sigma xx is c1x plus c2y, and so what are it? Tau xy. So tau xy is c5x minus c1y, and remaining things are 0. It should be equal to 0. So by this differentiation I'll get c1, and again I'll get c1 minus c1 equals to 0. So first equation has been satisfied. C1 minus C1 equals to 0 equals to 0. So left hand side is equal to the right answer. Yeah. Are you able to hear me? Is there any network problem? No, right? I think I'm audible. Just yeah, okay. The next equation again we have here we have tau yx. So tau yx we have c1y minus c4x plus dou by dou y into sigma yy. So sigma yy we have c3x plus c4y, and again as body force and z component whatever it is 0. So we have minus c4, and we'll get again here c4 equal to 0. So 0 equal to 0, again the second equation is satisfied. Second force equilibrium condition is satisfied. And third, we have sigma x dou by dou x into tau xz. I think this we know, this we don't need because everything is 0 here. So third equation will be automatically satisfied because every z component we have is 0. So all the three equilibrium equations have been satisfied. Force equilibrium equations have been satisfied. Now we have to go for moment equilibrium. So moment equilibrium, we should have these all these things, all these three equations should be satisfied. The cross shears, we call this as cross shears, whatever the tau x y y x. This should be equals to this. This should be equal to this, and this should be equal to zx equals to x. So these the equation should be satisfied. So here we have all the cross shears. So this and this is 0. It will get satisfied, and this is 0. These z components, whatever 0, 0. So these two equations will be automatically satisfied. And this equation, we have sigma xy. Xy is we have c5x minus c1y equals to c1y minus c4x. So this should also be satisfied in order to satisfy the moment equilibrium condition. So here we don't have any information uh, about what these values are, and we should have some extra conditions to get these constants, and that's why for any arbitrary values this cannot satisfy. There should be some extra condition which should be satisfied. There should be some extra condition by which we can prove this, because it's not simply possible to so, uh, show this equation or equilibrium condition is satisfied with the information we have. So that's why, because this condition is not being satisfied, we can say that all force equilibrium conditions are getting satisfied for all the values of C1, C2, C3, C4, whatever you take. But the moment equilibrium condition one doesn't get satisfied for any arbitrary value of C1, C2, C1, C5, and C1, C4, something arbitrary value of constants. That's why we can say that this stress tensor is not possible here. So it doesn't represent the elastic deformation at any point on the body. So if this was satisfied, again we could say that this stress tensor represent deformation at any point on the deformed elastic deformation on any point on the body. So this is how we check. So if all the conditions are satisfied, then we can say that this stress tensor will represent elastic deformation at any point on the body. So this is the first thing. The B part also, I think we'll look at this too. I guess there are no doubts in this part. So if you have any, please let me know. Okay. So again, we have the three equilibrium conditions here. Simply, we have sigma xx equals to minus 3 by 2 x square y square, and sigma xy or tau xy equals to x cube. So again, here sigma xy is equals to yx. So I'm writing it as it is. Sigma yy is equals to minus 1 by 4 pi power 4. So the moment equilibrium condition is already satisfied. So we don't need to check here. So cross shears are equal, and in the other planes are also other planes too. The cross shears are equal. So these three conditions will be satisfied in this case. First, okay, we need to only check the first two force equilibrium conditions, because third will be automatically satisfied. So rho by dou x of minus 3 by 2 x square y square plus rho by dou x dou is x by 3 equals to 0. So I'll get 3 by 2 into 2x, and plus 3 into x into y square. This 2 to left hand side. Get, oh, we have here y also. Yeah, this is square, sorry. Yeah. So minus 3xy square plus 3xy square is equals to 0. So the first equilibrium equation, force equilibrium condition is satisfied. Similarly, I have the second equilibrium condition, dou by dou x of tau xy plus dou by dou of sigma yy. So sigma yy I have minus 1 by 4 by power 4. So y cube, again this will be minus y cube. So second equation is also satisfied. Third will automatically satisfy because all the z components are 0. So all the force and moment equilibrium conditions are satisfied. That's why we can say that this stress tensor will represent elastic deformation at any point on the body. So this stress tensor is possible. The first question which we have solved was not possible because moment equilibrium condition was not satisfied for any arbitrary values of the constants. So I think this is clear. Yeah, this is clear. If you have any doubts, again please ask.
No, sir.
Yeah, okay. So I think we'll go to the next part. So next part is the most important, one of the most important thing. The questions which you are uh, going to solve in Morse circle. Morse circle is extremely important because people easily get confused in this part. And this is actually Morse circle is the most asked uh, or most interrogated thing in interviews whenever you sit for, I think, if you go for any PhD or tech interviews, you have a very good chance that you will be asked some questions about moon circle or something, things which are related to it, because it 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 gives a very good idea of how the understanding of your subject is using this concept of moon circle. So whenever you have the, and also in gate examination too, there is a very good, very high chance of getting questions with a uh, which are based on Moore circle, because because gate is an aptitude exam, so uh, it basically they won't give you you have 1 or 2 marks questions, so you have to solve, like, there is not very, like, you don't have to solve a big problem. So more circle is something they can test your aptitude, by which they can test your aptitude very easily. So this is the problem. Uh, Here we have to draw the Moore circle and write the stress tensor for the following given state of stress. So again, so I'll just take a 2D element here. 2D element. In 2D, we have sigma xx. If I take the orientations like this, as he has given, as it is given in the problem, this is x-axis and this is y-axis. So plane perpendicular to the x-axis is explained, and the normal stress acting is sigma xx, and this is sigma xx. This is sigma yy. and this shear stress which is acting on the x plane, and direction is in the y direction. So this is tau xy and this is tau yx. This is also tau xy and tau yx. Okay. So by comparing these two, I can write this stress tensor like this: sigma xx, tau xy, tau yx, and sigma yy. Okay. So from this, by comparing these two, here we don't have any normal stress on the x plane. That's why sigma xx is 0 here. And we don't have any normal stress on the y plane too. That's why sigma yy is also 0. And we have tau xy, which is given as 20 megapascal. And here again we have tau yx is 20 megapascal. So this is our stress tensor. Okay. So now we will go to the Mohr circle part. So Mohr circle, I'll just give an idea of how we draw. We will draw a Mohr circle for a. Okay, so this is a coordinate system, and in this coordinate system, on the x-axis we will take the normal stresses, and on the y-axis we will take the shear stress tau. So, and this is the origin. So if you have this, so if you have this state of stress on any body, so this is the state of stress. For this, if you want to draw a Mohr circle, so first we have to first thing we have to do here is, so we have the xx and tau x. So any point, uh, so you know sigma xx. So sigma xx, let's say this is sigma xx value, normal stress acting on the plane, and you know the shear stress acting on this plane, which is tau xy. Okay, I'll just this tau xy. So this is the state of stress. This is the stress on the x plane. So and now again we'll go to the other plane. We have sigma yy, and on that plane, let's say I'll just take this in negative direction. You can take this interchangeably. It doesn't matter like how you take it. And this is tau yx. Okay, and we have drawn the state of stress on x plane and y plane, and these 2 points are representing. So in the 2D Mohr circle, because this is a 2D element which I have taken, in this in this we have whatever this point and this point is representing. This point is representing this plane, okay, this plane, and this point is represented by this plane. So now, in order to draw the circle, I have to join these 2 points by this line, like us taking a straight line. Join this point, join these 2 points, and using this as center and this as radius, from this point to this point as radius, take a protractor, and we have to draw this circle. So sorry if you think my drawing skills are bad, because this is on an iPad and do like this. So circle is coming very bad. So this is this is an ellipse, but you assume it as a circle. So this is the way to draw more circle. Or I'll just okay, okay, I'll do one thing. Just taking some time. Okay, sorry. Okay, so this is this is tau xy, and if I say this is sigma xx, and this is tau yx. And joining these 2 points, this point and this point, this point and this point, this is the center of the circle. So from this center and taking this as radius from this here to here, you have to draw a circle. So this is the Mohr circle, and every point on the circle will give a plane. So every point in this circle will give me a plane on which uh, will give me a plane on which the stress and normal stress and shear stress can be identified. So this point is the x plane and this point is the y plane. So on this circle, uh, I have this point on x-axis, or you can say the normal stress axis. At this point, the shear stress is 0, and we have maximum normal stress. This point is the principal plane, and this point represents the principal plane. So principal planes are the planes on which only normal stresses are acting, and this point is the another principal plane. Here also shear stress is 0. This point is also an another principal plane, and because here the normal stress is maximum, you can say uh, primary principal plane, and this is the secondary principal plane. You can say it like that. And if you see here, if you see here on these 2 points, on the top and on the bottom of the circle, here the shear stress is becoming maximum. So whenever the shear stress becomes maximum, uh, it uh, it doesn't have to be like uh, it doesn't need to be such that uh, normal stress is 0. Whenever the shear stress is maximum, we don't have any requirement that normal stress is 0 here. Here you can see there is normal stress, some normal stress here, and also shear stress is maximum. But whenever we come to principal planes, the normal stress is the only component which is present, and shear stress is 0 at both these points. So now we come to this problem. So for this, we have to draw the, if you want to draw the, okay, Mohr circle. Here we don't have any, normal stresses given. So normal stresses are both 0, and but we have the shear stress which is 20 megapixel. So normal stress is at origin, and this normal stress is 0. From that's why I'm going in the y direction. So this is 20 megapixel, and this is 20, sorry, 20 megapascal, and this is also 20 megapascal. So normal stresses are 0. So, and you know the radius is also here 20 megapascal. So using this, we can draw the Mohr circle like this. Okay, and when see this, these are the principal planes for this. This is how we draw the Mohr circle. So you have to take, as I have explained here, you have to take this and draw whatever the state of stress is taken, sigma xx, tau xy, and again sigma yy, tau yx. Join these 2 points, draw a line. Whatever, wherever this line is intersecting, you take this as the center of the circle and this as the radius and draw a circle. Okay, is this fine? I'm sorry if I have made it a little bit confusing due to this diagrams and other things, but I think you have got whatever is written here. Yeah. So now we have got let's say we'll calculate what is the principal stresses for this. What are the principal stresses for this state of stress which is given. So and we'll find out what is the angle at which the angle of the plane at which principal stresses are acting. Okay. So this is the plane, and these are the planes which are given in the problem. So this one and this one, 20 megapascal, 20 megapascal, and these are the principal planes. And what is the value of that which we have to calculate? So here you can simply say that we don't need any extra calculation here. You can simply see that if this is 20 and this is origin is the center, this will also be 20 and this will also be 20. So sigma 1, which is the major principal stress, you can simply write as I'm not writing a formula here, just or we can use a formula also. Okay, I think you all knows this basic formula which was explained in the class. Sigma xx plus sigma yy by 2 plus root over sigma xx minus sigma yy by 2 whole square plus tau xy. Here xx and yy are 0, so this is 0 and this part is also of the root becomes 0 and this 20 root square 0. So 0 plus 20 square whole root. So sigma 1 can be simply written as 20 megapascal. But you using this diagram, if you have this Mohr circle, do you need any a formula which you have to remember to calculate the Mohr circle? This formula sometimes it becomes harder to remember, but as time goes by, you can remember this. But simply using this diagram, if you have drawn this diagram, you can simply calculate what is the principal stress at this point. And similarly, sigma 2, from this you can write, from this you can calculate as same formula. Here minus, you will get minus 20 megapascal. So, and the plane at which this thing is acting. Okay. Here, this plane, principal plane, is at a angle of 90 degrees, 90 degrees from the x plane. So, in the Mohr circle, this angle is 90 degrees. But whenever we come to the actual representation, this angle will be half of the angle in the Mohr circle. So this will be 45 degrees. So the principal plane will be at an angle of 45 degrees from the x plane. So this is one principal plane, and another principal plane is this. So both these two are the principal planes for this part. You can simply see that this is the state of stress, and these two planes are principal planes. On these two planes, the normal stresses are maximum and minimum. So, I think you can imagine this. These these two are these two shear stresses are uh, this is like this, and you are squishing this like you are these two shear stresses are dragging this like this. So this will let's say it will deform like this. So it will deform it. So here, due to this squishing, this is the acting. This is the normal stress acting. And here, this is compressing it, and that's why we have sigma 2 negative. I hope you can visualize this. This is dragging this like this, and in this direction it is getting compressed. Here it is getting pulled, and here it is getting compressed. Yeah, that's how you got the Morse circuit. So in the I think we have time, so we'll go to the next problem too. Or okay, so the concepts I I hope you all of you have uh, okay. You can take a screenshot of this question uh, because I'll just move it. This we have already solved. So the question is like this: a metal bar, a rectangular bar of metal having cross section of 30 by 30 is subjected to an axial tensile force 150 kilonewton in y direction. So and there is a normal given which is having this direction cosines. So we'll just draw a diagram. So this is the metal bar. Let's assume this is the metal bar. And let's say this is the orientation which I'm taking. This is x and this is y. And this is having cross section. I'm not drawing this in 3D. So I hope you can visualize what is the cross section. So which is having an area of 30 by 30. Yeah, mm. And it has a tensile load of 150 kilonewton acting like this. So the thing is, because the tensile load, whichever I am applying, okay, let's do one thing. From this bar, the load is same at every point on the bar. So I'll just take a small, small point, or if I zoom it like this, let's say I can take a square like this. So on this, the stress due to the load applied is, so first let's say we'll calculate the stress, okay? Because this is in y direction, tensile load is acting in y direction. Sigma y is equals to P by area. So cross section area is given, load is given. Just calculate whatever you have, 30 into 30. Because these are in mm. I'll just, okay, I'll just take, because this is in megapascal, whatever the stress, megapascal means Newton per mm square. So I won't take this. Yeah. So if you do this, you will get sigma yy is equals to 150 to 10 cube divided by 30 into 30. So what do we get here? 166 point, let's say 67 megapascal. So this is the stress acting on this bar element. 66.67. Same here. And other components are zero. I've taken it. So the stress tensor of this can be calculated, can be written like this: 0.167, 166.67. So, and he's saying that there is a uh, if a plane whose normal has direction cosines like this, for that given direction cosines are 0.0000707 and 0. So this is cos alpha, this is cos beta, as I've said. So Kishore, so all the recordings of these sessions are posted on YouTube, and you can get if you go to NPTEL in Swayam. So below in on the left hand side you can see problem solving session. So if you click that, you go to all the files and all the recordings of that session. Okay, or you can say, or you can just search my name Syed Shabbir Ahmad IIT. You will get the YouTube channel. Okay, so there the recordings are there. So these are the direction cosines which are given, and from this so this is the bar, and he's saying that there is a plane which has the direction cosines like this, and if we have the direction cosines, I can get the normal of this plane. So normal of this plane can be written as 0.07 I plus 0.07 j cap. Yeah.
So,
Yeah.
can I ask something?
Yeah. Yeah. Please go
Uh,
ahead.
Sir, what if they are giving the only angle?
Angle. Yeah.
The,
Okay.
uh, सर
So let's say.
बेसिकली द माय डाउट इज कि
Hmm.
इसमें सर डायरेक्ट गिवन है डेटा लाइक
Yeah. Yeah.
व्हाट इफ दे आर प्रोवाइडेड एट एंगल सो
Yeah.
व्हाट
Okay.
शुड आई
Okay.
डू
Okay. Okay. So let's say they are giving something like this. Uh, okay. If they say that, let's say this is x-axis and this is y-axis, and if they said that the plane is at an angle of uh, some theta degrees, this is the plane. Okay. I won't confuse you with this 3D thing. Just assume that the plane is a line here.
ओके सर
Okay, this is the plane. Okay, and he's saying that plane is at an angle of 60 degrees from x-axis,
या
or let's say, or he can also say that plane is at an angle of 30 degrees.
30
Okay,
डिग्री
30 degrees from the y-axis. So for this plane, the normal will be perpendicular to it, right? This is the normal. Okay, this is perpendicular. So you have this is 30 and this is again 60. Okay, I hope you are getting this.
यस सर
So this is whatever the normal, whatever the normal is, whatever the normal is making an angle with x-axis is alpha, and whatever the normal is making an exact, whatever the normal, whatever the angle normal is making with the y-axis is beta. Okay, and okay, alpha beta. So the direction cosines are basically cos alpha and cos beta. Okay, yeah.
या गॉट इट
So here I think we don't need this from this normal which he has given uh, magnitude of component. Okay, we have to calculate the x component of the traction vector and y component of the traction vector. Okay, so I know the stress tensor and I know the normal components is 0.007. So if you multiply this, you will get this thing as 0 and this thing as 166. It is 0.707. So 117.835. Okay. So here Txn, this is x is 0 and Tyn and this is 117.835 megapascal. This is how we calculate the components of stress vector. Is it clear? I think I have done it right. If you have, yeah. So yeah. So I've cross checked. This is the x component of the stress vector on that plane, which is having this normal, and this is the y component of the stress vector. So the next thing is magnitude of the z component. Z component is 0. So Z component, because this is in xy plane, so there is all these other components are Z, all the Z components are 0. So the stress component in Z direction is also becomes 0. So that is also 0. And magnitude of traction vector acting on the plane. So magnitude of this traction vector is just simply uh, yeah, txn square plus txn square plus tyn square. So again you will get the same thing, root taking the root. Again magnitude of this is 0.835 something megapascal. Yeah, 117.835. Same thing. Same thing. Magnitude of the next thing is what is the magnitude of shear stress acting. So again we have to use this. What is the magnitude acting? For this you have sigma n square plus tau square. Because this and this are same, stress tensor stress vector magnitude and the normal stress component are same, 0 0. So here shear stress we will get 0. So the magnitude of shear stress is 0. Okay, yeah. Ah,
Sir,
yeah,
uh, how did normal uh, stress become same, sir?
normal stress becomes same. Okay. So we have calculated the traction vector, right?
Yes, sir.
Now, okay. Yeah, yeah, yeah. Sorry. Yeah. Okay. So, sorry, I made a mistake here. So, in order to calculate the normal stress and shear stress on the plane, so I have the traction vector or stress vector acting on the plane, that is Tn is equals to 0, and this is 135. So, in order to get the normal stress, I have to get the dot. I have to take the dot product of stress vector on the plane and also the normal vector on that plane. So, if I do the dot product, so again, so dot product means simply this is you can take uh, in matrix form like this, transpose, and this is it, n. Okay, so this is 0, 117.835. And this is 0.0707 and 0.707. And if you multiply this on 7.835 into 0.007. So the normal stress acting on the plane is 83.309 megapascal. Again, cross verify. Yeah, this is the normal stress acting. Now the shear stress, to calculate the shear stress, we'll use this formula. Sum of the square of the magnitude of stress vector is equals to square of the individual component, which is normal and shear stress components. So now you have tau, magnitude of tau equals to root over 117.835 square minus 83.309 square. Yeah. So now please do this. 835 square minus 83.8. So tau we will get, magnitude of tau we will get 83.335, let's say 335 megapascal. Yeah. This is the normal stress, magnitude of normal stress, magnitude of shear stress acting on the fluid. So yeah, so the answer matches with this. Yeah. Okay, I think this is clear. Yeah. Have any other questions? Have you verified this, Priyanka?
I got the same answer, sir.
Yeah. Okay. Okay. So okay, this is the whole part which we had discussion, and which we had the discussion, and okay, we have another question too. So here they have given the direction cosines as the last question. Direction cosines are 1 by root 3, 1 by root 3, 1 by root 3, and for this we have to calculate the normal magnitude of normal stress acting on that. So this is the normal for the plane, and we have to calculate the magnitude of normal stress. For that we have to calculate the traction vector again. So traction vector can be done like this. What's the formula? I think all you know. So here, because this is a 3D thing, I have to write this in a 3D form. So earlier we were dealing with only a 2D thing, so I was writing only a 2 by 2 matrix. Here you have to take a 3 by 3 matrix. 1 by root 3, 1 by root 3. So if you do it again, you will get this and 0 and 117.835 to 1 by root 3. 68.03. So in order to get the normal stress acting on this plane, I have to take the dot product of this vector, traction vector, and the normal again. So again, as I said, this is, you can write it like this, traction and n vector. So transpose means like 68.032 0 by 3, 1 by 3. So we'll get the normal stress acting on the plane as 39.27 megapascal. It right? Yeah, just verify that. Mhm. Okay, sorry. Again, we have done a mistake. So this is 166.67. Sorry, 166.67, and then this becomes 166.67 into 1 by root 3. This becomes 96.226, and again doing this at 55, ninety-six point two two six, and this I'll get 55.56 megapascal. So this is the normal stress acting on this plane, whose direction cosines are 1 by root 3, 1 by root 3, and 1 by root 3. Yeah. This is the whole procedure how we go about solving the problem. Next week, I think we have again more circle and lot of other stuff. So I think whatever the session which we have taken today, it helps somehow. I hope I have not complicated things. Uh, yeah, somebody is speaking. No? Oh. So I have given in the chat. I have sent a message. So to give feedback, if you are not like you can go, you can give feedback here. You can just turn on your mic, give some feedback. Or if you are not comfortable, then you can fill this Google form which I'm sharing in the chat. So in the chat box. So this Google form is like anonymous. So your details and all won't be uh, taken. You can give any suggestions or feedback which you have. So we will try to implement this in uh, our future sessions. So feel free to give the feedback. And somebody was asking me where these recordings will be uh, taken. I'll just share that link.
Hello, sir.
Yeah, yeah.
Sir, I have one doubt regarding which books I have to refer for, because assignments, as per my level, it is too much difficult for me. So I would like to refer some books. So can you please suggest me some books which can I
Uh,
read and solve the problems? Because I have seen so lots of books which is name is Kulmi and Ramamrudam also.
Mm.
but I got confused from them, and so please suggest me which books are sir referring, so I can do
Okay.
something.
This question, I think, have you joined the discussion forum?
No, sir, I haven't joined.
So in NPTEL, na, you can on the top when you log in NPTEL, on the top when you see the lectures in NPTEL, Swayam you have enrolled, right? There will be questions like ask a question, something. There will be a tab. You can join that forum and ask the professor itself. Because I also don't know. Because I think this is like a mixture of lot of books.
Yes, sir.
Yeah.
That I
Hmm.
definitely know. This
Yeah.
is a mixture of lots of books. So
Yeah.
basically, sir was talking about only theory, and but
Uh,
my problem is I
uh,
literally don't understand how to approach the question. There are so many questions I really didn't get to know. So that's why I have a doubt, sir. But I definitely, whatever you're suggesting me in, I'm
mm,
checking now.
yeah.
My course.
Uh, okay. I'll do one thing. Huh? I'll
Yes,
just
sir.
I'll share it. Share this.
Yes, sir. I got it. The discussion forum.
Got okay. Okay. Yeah.
Yes. There are
Yeah.
some doubts. Okay, sir.
Yeah.
I got it.
Yeah.
I
So
definitely
somebody will.
asked. Ha,
Hmm.
sir.
Yeah. So if you can ask that in the chat box because professor will keep a look on that. Hmm.
Okay, sir.
So the thing is like I don't actually any follow any book. So I don't like I don't have any specific book. But there is like the classical book which is like the most famous one is Timoshenko book by
What?
Timoshenko's book. Timoshenko. I Timoshenko. But this is like uh, not a very beginner friendly book. I would say.
Okay, sir.
But you can ask it. You can ask in the discussion forum that if I have to refer some book, what would you prescribe like that? They will suggest you some books based on that.
Sure, sir. Sure.
Are you watching the lectures like that?
Yes, sir. I have seen every lecture, but
Yeah.
still, I'm haven't done my graduation, and I'm doing so. Still, I'm
Okay.
getting
Okay.
a doubt.
In what in what year? In which year you are in? Yeah.
Sir, I am in second year.
Okay. 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 Okay.
Yeah, okay.
So that you have to uh, practice a lot.
Yes, sir.
Um, only thing which you will only thing which will help you in set of materials is practicing a lot of questions from different books, or you can
Yes.
then you will be comfortable in this. Yeah.
Yes, sir. Yes, sir. Sure, sir.
Somebody, yeah. Somebody was asking me where can you find the recorded lectures? I have shared the link here in the chat box, and this is like YouTube channel. You can find this. Okay.
Okay,
Yeah,
sir.
yeah.
One more.
Good evening. Yeah, yeah. Please
Yeah. Yeah.
continue.
Yeah, yeah. You can ask Kishore.
Yeah. Good evening, sir.
Yeah.
First of all, I very thank you for your such a wonderful session. Because last time I
Yeah.
have not attended the session, and because of that I am not able to understand the problem, and I am not able to complete the exam for the last first week also.
Okay. Okay.
So I listen this session, and I'm regularly watching the session as our totally means loading the our app and all of things.
Okay,
So
okay,
definitely it will be more helpful to your sessions, and definitely I will continue this session in next week also.
okay,
Actually, I
okay,
didn't get the time for today. I have attend the last 1 hour only. So, but
okay,
definitely it will be more helpful to complete the uh, our session properly and understand the
okay, okay. Yeah. Are you? Am I audible? Yeah.
Yes, sir, you are audible, but
Yeah.
Kishore is not
Okay.
audible.
Okay. 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 So, so I have tried whatever I can, but so if you think these problems are very like very very easy or very tough, whatever you can, whatever you want, so just give me the feedback. We'll try to implement
Sure,
however
sir.
it goes. Yeah.
yes, sir,
Sure,
yes,
sir.
sir, definitely.
Okay.
So last doubt,
Yeah.
when this the today's lecture वो कब तक upload होगा sir?
ये आज ये वाला सेशन
Yes, sir. This today's session.
this will get uploaded by tonight, like let's say 12 or
Yes, sir.
something. So
Actually,
yeah,
I have missed something, so that's why I'm just asking you. That's fine. Today is the last date for submission assignments. Second wala.
I
So
Yes, definitely. My
okay,
last
okay.
assignment also pending because of the I'm searching some of the answer and some of the question, how to learn, how to solve the questions, because by randomly is not process means is not correct way to just click on the answer and just get marks. You can
Yeah, yeah.
understand means I have to understand what is the solution, how I can complete the session properly with the proper formula and all of things. So I'm also waiting, and I have to also complete the last two sessions exam also.
Okay,
Yeah,
okay, okay.
thank
It's fine.
you.
Yeah,
Yeah, yeah.
yeah. Okay, okay. I think if you are, if someone else has any question, like you can ask. Otherwise, we will wind up the session today. Yeah,
Thank you.
yeah. Okay, fine.
no doubt, sir.
Yeah. Okay.
Thank you,
Thank
sir.
you, bro.
Yeah. Okay. Take care. Fine. Yeah. Bye.
Thank you, sir. Thank you so much.